So we'll start off here discussing some strategies for solving equations, most of which are quadratic. If I give you an equation on this first one, x squared minus 3x minus 18 equals 0, and I ask you how to solve that, what would you try? You try factoring first because it is a quadratic. So if you try to factor this one out, keeping in mind all along it's equal to 0. Now let's see, this one would factor to what? 6 and 3. So if we do minus 6 plus 3, there's the factored pieces. And then as we understand with the factored pieces, since all of this equals 0, we set each factored piece equal to 0 and we solve from there. Obviously x is going to be 6 and x is going to be negative 3. So you can box those in. Or if you want to be real official-like, you can make this little set notation and form our solution set for our answers. As long as you highlight somewhere that you got 6 and negative 3, we're good to go. So there's the basics of just factoring a quadratic. Now, other situations where we've got quadratics, maybe it's set equal to 0, maybe it's not. Let's try this one. Got to keep in mind some other strategies. So say here we have x squared minus 4x minus 1 equals 0. The first approach you should use on these is make sure everything equals 0. Okay, we have to make sure everything equals 0 first. Then try to factor. If factoring is not a possibility, like factoring would not be a possibility here if you tried it, what's the next choice? Quadratic formula. So quadratic formula, as a review, got negative b plus or minus square root of b squared minus 4ac all over 2a. On this one, a is 1, b is negative 4, c is negative 1. If we plug in, x is going to equal negative b. We have a negative 4 as the b, so that becomes positive 4, plus or minus, square root of b squared, the negative 4, all of that squared. That will become positive. Minus 4 times a, which is 1, times c, which is negative 1, all over 2 times a, 2 times 1. So we're plugging in the quadratic formula here because it's not convenient to factor. By the way, even if it was convenient to factor, could we still use the quadratic formula? Sure. Anytime you have a quadratic form, everything equals 0, you could still use the quadratic formula. But here we start doing some calculating. You got 4 plus or minus square root of. Discriminant value under that root becomes, what, 16? Be plus 4, right? Because of the 2 negatives here. So we got 20 all over 2. We should break down that root. Understanding here, we're getting an irrational answer, right? Anytime that root's left in there, answer is going to be irrational. So breaking down the root, 20, perfect square that goes into 20 would be 4, right? So take the square root of that 4 being 2. You got your 5 left over under the root. Meantime, this is all over 2. You've broken down the root. Now you just look to reduce a little further if possible. Notice between the 4, the 2, and the 2, you got a common factor shared. That common factor, of course, would be 2. So if I divide 2 into all those, I would have 2 plus or minus just the root 5. And that would all be over 1. So there's your solution for x on this one. So anytime we've got a quadratic equation, we can use the quadratic formula, whether it's factorable or not. We just usually look to see if we can factor to start, because a lot of times that's just a little more efficient. Questions there? Hopefully not, since this is a review, right? All right, we'll try this one. Got another equation here that appears to be some sort of quadratic. We've got 4x squared plus 3x equals 10. Based on what we reviewed on the first two problems, what would you start by doing here?
So move the 10 to the other
Move the 10. There we go. We've got to move the 10 over. So when you move the 10, you're subtracting that 10 over. Now that everything equals 0, this is where you look to maybe factor. Or if this is something that you just don't want to factor, you could use the quadratic formula. Which would you like to do? Quadratic? All right, here we go. Carrying over the strategy from the previous problem, you start with the negative b. b on this one's positive 3, so it's negative 3 plus or minus square root of b squared, so 3 squared, minus 4 times a is 4, times c is negative 10. All over. 2 times a, that'd be 2 times 4. X equals negative 3 plus or minus be the square root of, now let's see, 3 squared goes to 9. We got a whole lot going on here, right? You've got a negative 4 times 4, which is negative 16, times negative 10, which would be positive 160. You're adding 9 to positive 160. That'd be 169. All over 8. You can take the square root of 169. That is 13. So since the radical disappears, this tells you that originally we could have factored this, right? That would have been possible because we're going to get rational answers here. Either way, you are adding or subtracting the 13, so take it one piece at a time. X is going to equal negative 3 plus 13, which would be 10, right? 10 divided by 8 is 10/8. Reduce that to 5/4. And then subtract negative 3 rather, minus 13 be negative 16 all over 8. That'd be negative 2. So you could have factored it, but either way, we've got our answers. All right, we'll try one more here of these equation types. This is not going to be a quadratic, though. Make us think a little bit on this one. Really what we have here is a cubic if you rearrange things correctly. Speaking of rearranging things, what would you do first? Add the 4x over. Subtract the 12. So set everything equal to 0, right? If you set everything equal to 0, you've got x cubed minus 3x squared. You're adding the 4x, subtracting the 12. Now that everything equals 0, what would you like to try? Okay, factor by grouping because you got 4 terms. We could try that. If you group these, in the first grouping we pull out an x squared, leaving us with x minus 3. If this is going to work, in the second grouping we also need an x minus 3 left over. That would work, it looks like here, if we pull out a 4, right, a positive 4. So completing the factoring by the grouping, we take the x minus 3, we can shove that to the front. What would remain would be this x squared plus 4. All that equals 0. So if you take each factor, set each factor equal to 0 and solve from there, on the left side, x equals 3, obviously. Right side's a little more intriguing because x squared would equal -4. It didn't say anything in our directions about not having real solutions. So if we took the square root of each side, we're taking a square root, so you got plus or minus. And let's see, you'd have the square root of 4, which is 2, but it's negative, so what do I include? An I, plus or minus 2i. You might recall on these problems once upon a time that when we started off with something like this as an equation, we were asked to find the zeros, right? Or the roots, because this is an equation, the roots would actually make a little more sense. And we knew how many roots to find based on the degree of the polynomial. Since there's a degree 3 on this one, we've got 1, 2, 3 solutions. And it wasn't always the case on these problems, but sometimes you weren't able to factor them. So when we weren't able to factor them, this is just a strategy to keep in mind in case the problems you face aren't all factorable. You could take this polynomial right here, this cubic, and graph it. So let's see, is this going to work for me? Nope. So if we graph this out, right, there's the function. Graph it. We should notice that it's crossing at 3 on the x-axis. Makes sense because that's one of our solutions here. And had this not been factorable, what we would have done is we would have taken that value where it crosses the x-axis. We would have taken that 3, and over here, we would put the 3 in the box. You'd spell out your coefficients from your cubic right here. So 1, -3, 4, -12. Assuming that 3 works with this synthetic division approach, we get 0 back over here, assuming 3 is a root. So you bring down the 1, multiply back to the box, get 3 there, add through, get 0, multiply back to the box, get 0, add through, get 4, multiply back to the box, get 12, and we get 0 back, right? So we went from something that was a degree 3 in this level to a degree 2 down here, meaning x squared plus 4. If we set that equal to 0 and solve, we get our remaining 2 solutions. We didn't have to do that on this problem because it was factorable, but on other problems where you can't factor, you might want to remember that approach, okay? All right, for the next topic of review here, we're simplifying expressions, and more specifically, these expressions are going to be rational expressions. So an example of a rational expression, something like 2x squared plus 10x all over 4x. That would be a rational expression. We've got a ratio of 2 algebraic expressions. As we review how to break this one down, any suggestions? Okay, do some factoring, right? If you look at the pieces in the numerator and denominator, see if you can factor them down further. In the numerator, you can take out a 2x, right? That's the greatest common factor. If I take out a 2x, what's left is x plus 5. That would all be over this 4x, which I really can't do much with. Whenever we have rational expressions, as long as you have factored pieces to play with, then you can do some reducing. You can do some canceling. So since this 2 is multiplied to this x, which is multiplied to that x plus 5, and down here this 4 is multiplied to that x, the 2 and the 4 you can reduce, right? 2 goes into itself once, into 4 twice. The x's, we can cancel those out. If you write what remains, you've got x plus 5 because that's just multiplied to 1 all over just 2. That'd be your simplified expression. So the key to simplifying a rational expression is making sure it's completely factored. Once it is, then you can start canceling things out. If we try another. This is just additional good factoring practice compared to what we were discussing yesterday. Got a quadratic expression, 2x squared plus 11x minus 6 all over x squared minus 3x minus 54. If the rule is make sure everything's factored out, should know what to do with this. Start with numerator or denominator, doesn't matter. Either way, let's try to factor these out. In the denominator, you've got a lead coefficient of 1, so that might be a little quicker for us. Since that lead coefficient is 1, we know we've got x, and x is the setup. And then what's the last term going to be? 9 and 6. If we make that a minus 9 and a plus 6, we should be set. Now think about where you're going with this. If we know this is the factorization for the denominator, hopefully things cancel out in the numerator. We should have some sort of common factor or common quantity on top when we factor the 2x squared plus 11x minus 6. So if I break that up, we know in the lead positions it has to be 2x and x to give me that 2x squared. In the last positions, once again, looking at where I'm trying to go, needs to multiply to give me 6. So factor pairs, you got 2 and 3, you got 1 and 6. But looking at where I'm going, I've got a 6 down here, right? So maybe 1 and 6 might make sense. And if you check this, outside is 12, inside is 1, that would create the combination of 11 that I need. So the outside would have to be positive, the inside would have to be negative. Now that everything's factored completely, you take your multiplied pieces between the top and the bottom, cancel out the common ones, the x plus 6's go away. You are left with 2x minus 1 over x minus 9.